Hello and welcome to physics. Today we'll discuss about motion. I am Mehdi Hassan Chaudhary. I'll be with you for the next of the whole topic, and today we'll dive deep into motion and understand different kind of motion. After the end of the topic, we'll able to explain rest and motion, analyze the relation among the quantities regarding motion. We can find out the difference among different types of motion. We can explain the motion of freely falling bodies that we can apply Galileo's law in for freely falling bodies, and we can analyze the relations among the quantities of motion from graph, and we can explain the scalar and vector quantities, and finally we can realize the effects of motion in our everyday life. Alright, in this section we're going to talk about rest and motion. To understand what is called rest and what is called motion, we have taken two horizontal path A, B and C, D. We placed to block X and Y. X is at the top and Y is at the bottom as shown in the figure. After some time, we see the box X is standing still and box Y is moving respect to its horizontal path CD. So you can easily say X is at rest and block Y is in motion. So in the sense of physics, we can define when a body is said to be at rest with respect to its surrounding when it doesn't change its position with time. And we're going to define motion as a body is said to be in motion with respect to its surrounding when it is changing its position with time. Types of motion. In our everyday life, we experience different kind of motion, but in this topics we're going to talk about some certain types of motion, like a linear motion, rotational motion, rectilinear motion, periodic motion, and vibratory motion. Linear motion. This is one of the simplest motion. So before I define your linear motion, let's take a look on this example. I have taken a straight path AB and also taken a block at the point A. After some time, the block is moving along this path AB, and if I wish, I can't move this block upward or downward because the motion is restricted in this path AB. And this type of motion is called linear motion. So we're going to define linear motion as if the motion of an object or a body is restricted in a straight path is called a linear motion. For example, the motion of a rail in a railway track or a motion of a bus in a straight street, and all these are examples of linear motion. So one thing, keep that in mind. Before we consider linear motion, we must not keep in mind or must not consider the motion of the wheel of this bus or the train as well. Translational motion. This is one special kind of linear motion. Take a look on this airplane. This airplane is moving along a curved path. When this airplane moves along this curved path, there's a little spin on this airplane. So every particle on this airplane doesn't move the same distance in same direction. The point on the upper wing travels more distance than the point on lower wing. So there's two curved paths show the difference of upper wing and the lower wing. So every particle on this plane doesn't move the same direction at the same time in the same amount. I'll take a look on this another plane. This airplane is moving along a straight path. Every particle on this airplane travels the same distance at the same time in the same direction, and this type of motion is called translational motion. So we're going to define translational motion as when a body moves along a straight line in such a way that each particle of the body travels the same distance at the same time in the same direction. If you place your mobile phone in a smooth surface and slightly push further without rotating the mobile, then this motion is also called the translational motion, because all the particle in your mobile phone doesn't change any direction. All the particles move the same direction at the same time in the same amount. An important type of motion is circular motion. A lot of objects around us showing these properties of circular motion. For example, a clock. Generally, a clock has three hands: an hour hand, a minute hand, and a second hand. A second hand takes 1 minute to complete one rotation. Similarly, hour hand takes 12 hours and minute hand takes 1 hour to complete one complete rotation. Every hand on this clock had one thing in common: the center of rotation, and it rotates focusing the center of this rotation. So every particle of these hands maintains same distance from the center of rotation. We have taken another pedestal fan, for example. This fan also rotates, centering this center of rotation or axis of rotation. All the particles on this blade maintain the same distance from the center of rotation and move a circular path. And take a look. One of the most beautiful example of circular motion is our Earth and our Moon. Our Moon rotates around our Earth, maintaining the same distance from this Earth, because the Earth is at the center and Moon revolves around this Earth and maintain the same distance from Earth. And this is one kind of circular motion. So we're gonna define circular motion as when a body rotates around a particular point or an axis, keeping the distance of the particle in the body unchanged, it's called circular motion. And there's a lot of examples we experience in our everyday life as circular motion. The topmost tip on a topic in the realm of physics is periodic motion. To analyze sound waves, electromagnetic waves, or to find out the life cycle of a radioactive material, we must need to understand what periodic motion is. That is, in every branch of physics, periodic motion is widely used. So, the motion of a celestial bodies or the vibration of a spring also shows the properties of periodic motion. Understanding simple harmonic motion requires deep understanding of periodic motion. Okay, we have taken the clock again as an example of periodic motion. So, this motion is also a special kind of circular motion with a definite time interval. We know every hand of a clock repeats this motion with a fixed time interval. That's why the motion of a clock hand is periodic motion. We'd like to recall our planet and moon for this type of motion. The moon revolves around our Earth, maintaining a certain time interval again and again. So we can say, if the motion of a body, a moving particle, is such that it passes through a definite point along the path of its motion in the same direction in a definite time interval, this type of motion is called periodic motion. In shortly, we can say the repetitive motion of a point with fixed time interval is called periodic motion. For more example, we can say the motion of Earth around the sun, and the motion of a piston in the cylinder of an engine, or our heartbeat. All are the example of periodic motion. In our daily life, we measure a lot of things, like the temperature of your body, the distance from the station, or if you're gonna go in your grocery store buy some sugar. All of this physical quantity can be measured with a certain number, like the temperature of your body is 98 degrees Fahrenheit, or the amount of sugar you bought from a grocery store is 5 kilos, or the distance from to station is 12 kilometers. So to measure our physical quantity, we use a magnitude and a unit. For example, I said earlier that 98 degrees Fahrenheit of your body temperature, 98 is the magnitude and Fahrenheit is the unit. So a lot of things we measure, but not every feelings can be measured, like our pain, our sorrows, our feeling, our happiness. The quantity which can be measured in terms of number, these are not physical quantities. So physical quantities are those which can be measured. And in physical quantity in our everyday life, some need only magnitude and some need magnitude and direction only. The quantity which regards and needs both magnitude and direction are called vector quantity, and the quantity which can be represented with the help of a number is called scalar quantity. The scalar quantity doesn't require any direction. For example, let me show you this school. This is 1 kilometer away from point O. If someone asks me how to go to the school, and if I say him that it's only 1 kilometer away, so he may go many directions. He may start from this direction, he may go to this direction or this direction in 1 kilometer. If he go any direction with 1 kilometer away, he can find the school, unless if I tell him or her the exact direction. So some physical quantity needs both magnitude and direction. If you start from O and go 1 kilometer straight to right, then you're going to find the school. That's why vector needs both magnitude and direction. So physical quantity which requires both magnitude and direction is called vector quantities, and physical quantity which doesn't require any direction, only magnitude is enough, this quantity is called scalar quantity. For example, the speed, the mass, the volume, or distance, all are the example of scalar quantity. And for example of vector quantities, acceleration, velocity, and electrical intensity, and a lot of example I can give you. So how you're going to define and how you're going to represent vector quantities? We use arrow upper of the letter or down of the letter, and this way we can represent vector quantities. So in our previous topics we have talked about scalar quantities and vector quantities, and we have defined that scalar quantity doesn't require any direction, only magnitude is enough to represent a scalar quantity. On the other hand, vector quantity requires both magnitude and direction. To clarify more about vector quantities, take a look on these topics, and this is distance and displacement. Distance is familiar word in our everyday life, but displacement is not. To clarify more about distance and displacement, have a look on this example. There's a curve path and there's a point O, 1, 2, 3, 4, 5, and 6, and every point is 1 kilometer away from every point. Okay, a man starts his journey from O to point 1. So we may say the distance is 1 kilometer. After a certain time, he moves along this path and reaches point 2, and the distance is 2 kilometers. Distance doesn't require any direction because it's a scalar quantity. So what is the displacement? The displacement is the path starting from point O to straight line to point 2, as I have shown in this red line, and the displacement is O to point 2. After a little bit later, the man go along this path and reach point 3, and after some time he may go to the path 4, 5, and finally at the point 6. So what the displacement is? The distance traveled by the man is 6 kilometers away from point O, but the displacement is from point O to from point 6, and this is the displacement. So displacement doesn't require which way and how many curved path you have passed. Displacement is measured from starting point to ending point. So distance may be greater, but displacement doesn't. So there's the difference between distance and displacement. So distance is a scalar quantity. It may be a long path, but displacement is a vector quantity. It denotes from starting point to ending point, not the other point. So I hope you get clear idea about distance and displacement. Generally, we all know what speed and velocity is. We use these two terms in our daily lives. To refer speed and velocity means how fast an object is moving. The greater the motion, the greater the speed. But in terms of physics, there's a little bit difference between speed and velocity. And the difference is speed is a scalar quantity and velocity is a vector quantity as well. So we're going to define speed as distance traveled by an object over time is called speed, and displacement traveled by an object over time is called velocity. Though displacement is a vector quantity, then velocity is a vector quantity. So suppose and the unit of speed and velocity is the same, meter per second. Suppose a car moved 100 meter in 20 seconds, then the speed of the car is 100 over 20 is 5 meter per second, and the velocity of the car is the same, 100 over 20 equal to 5 meter per second. Now in a straight line, the speed and velocity remains same, because in a straight line a car or an object can change its direction, and that's why speed and velocity in a straight line remains the same. Always remember, in the speedometer in our car, measure the speed, not the velocity, because speedometer can't measure the velocity or can't measure the direction of a car. That's why speedometer measures the speed. Always remember, velocity can be measured in a speedometer. Another familiar word in physics is acceleration. If you know how to drive a car or a motorbike, you must know what acceleration is. Suppose there is a car on the road. Initially, velocity of the car is lower. As time increases, the velocity of the car starts increasing. Suppose at the first second, the velocity of the car was 2 meters per second. Next second, it was 4 meters per second, and in the third second the velocity increases to 6 meters per second. So we can see that in every second the velocity of the car is increased by 2 meters per second. Thus the acceleration is 2 meters per second squared. The unit meter per second square is the unit of acceleration. It's a vector quantity. Now we can define acceleration as the rate of change in velocity over time is called acceleration. If an object is moving at a constant speed, then there is no acceleration, because no change in velocity means zero acceleration. But if a body rotates constantly, then why it has an acceleration? Okay, there's a table fan which rotates constantly. You can see that. We can see that even the speed of every particle of the fan is constant, but every particle is changing its direction over and over. There's constant rotation object has, and that's why constantly rotating object has an acceleration. The decrease in velocity over time is called deceleration. When you press the brake of your car, the velocity of car starts decreasing. This is called deceleration. Acceleration is denoted by lowercase a, and as we mentioned earlier, it's a vector quantity. Well, I want to make you more clear about acceleration and deceleration. From the help of a graph, I'll make you more clear about what's the difference between acceleration and deceleration from graph, and how we analyze acceleration and deceleration from graph. We have plotted a graph. This is time versus velocity graph. In the x-axis, time is plotted, and y-axis, velocity is plotted. So every point in y-axis indicates a change in y-axis is change in velocity, and change in x-axis indicates a change in time. So at the beginning of the time, this point is 0, and a little bit later the velocity of the car is increased and reached to the point there, and we can see that the final velocity of this object is greater than initial velocity. That's why there is a positive change in velocity. The positive change in velocity is called acceleration. So this point and this region indicates the acceleration of this object. Now there's a horizontal line in the next section. The horizontal line indicates there is no change in velocity. If there is no change in velocity, then there is no acceleration. From the definition of acceleration, no change in velocity over time is called acceleration. If there is no change in velocity, then there is no change in acceleration. So there is zero acceleration in this region. So in every horizontal line in time versus velocity indicates that there is no change in velocity, there is zero acceleration. On the third portion, there is also the initial velocity is here and the final velocity is there. So we can say that final velocity is greater than initial velocity. There is also an acceleration, because b final minus b initial over time indicates a positive change. The positive change in velocity indicates the acceleration. Now in the last segment, we can see that the initial velocity of this car or an object is greater than the final velocity. I plotted here. So there is b final is less than b initial, and there is a negative change in velocity. The negative change in velocity is called deceleration. So on this portion we have sketched there is the deceleration or retardation. So graph that downward line of time versus velocity graph indicates there is a deceleration. So from this graph, I hope you get a clear idea about acceleration and deceleration. To solve different kind of problems regarding motion, we use four equations. The first equation is b equals to u plus a times t. B here is the final velocity, u is the initial velocity, and a is the acceleration, and t indicates the time. And this type of equation is used in constant acceleration. The second equation we use here is called s equal to u plus b over 2 times t. S here is the displacement traveled by an object or a car or anything else. U is the initial velocity, b is the final velocity, and t is the time here. And u plus b by 2, this term is called average velocity. Sometimes it is used as s equal to b bar t. B bar is the u plus b by 2 over 2. When there is no change in velocity, we use this equation as s equal to b times t. So on the third equation, we use is s equal to u times t plus half of at squared. Here s is the distance traveled by an object, u is the initial velocity, t is the time, and a is the acceleration here. So for if a car or object is moving in a constant acceleration, we have to find out, and if you are given to find out displacement, then we use this equation. Now the final equation is b squared equal to u squared plus 2a time displacement. So b is we know b is the final velocity, a is the acceleration, and s is the distance traveled by an object. If there is no time is given, then we use this type of equation, and with this help of these four types of equation, we solve many kind of problem. One thing, keep that in mind, that in our everyday life, a perfectly moving body can be found because there is air resistance, there is a friction force. So in our laboratory, use air trick to make something a more accurate motion without resistance or without friction. Okay, here in this section, we're going to solve a problem regarding motion and how to use equations of motion in different problems. Okay, there is a question asked. A car started moving from rest for 6 seconds with 2 meters per second square acceleration. Find out the distance traveled by the car. So, in this problem, we have to find out what quantity is given. The given quantity is initial velocity, that is a car started from rest, and time is 6 seconds and acceleration is 2 meters per second square. And find out the distance. We have to find out s, or distance traveled by the car. Okay, put the value here. Initial velocity of the car is 0 because this car started from rest. We know something started from rest is initial velocity is 0, and it's traveled for 6 seconds. So the time is 6 seconds, and the acceleration of the car was 2 meters per second square. So the acceleration a is 2 meters per second square, and we are asked to find out the distance, that is s equal to what. So from this given quantity, we know this quantity is fit for the equation s equal to ut plus of half of at squared. Now we put the value here. Initial velocity is 0, time is 6 plus half of acceleration is 2, and time is 6 seconds square. After calculating, we find s equal to 0 plus half of 72, and finally we get s equal to 36 meter. So distance traveled by the car is 36 meter, and by this way we solved many problems regarding motion using this four type of motion. Galileo Galilei, the father of modern astronomy, discovered three laws for freely falling bodies. When an object falls from a certain height without other force act on it, is considered as freely falling body. We can see when you drop an apple, it will fall to the ground because of gravitational pull, and there is acceleration due to gravity, and in Earth, which is generally 9.8 meters per second square. Observing this incident, Galileo Galilei discovered three principles. And the first principle said all bodies falling from rest and from the same height without any resistance traverse equal distance in the same time. In the second law, he stated that the velocity acquired by a freely falling body from rest in a given t is directly proportional to the time, that is, velocity is proportional to the given time. And the third law, he stated that the distance traversed by a freely falling body from rest in a given time is directly proportional to the square of the given time, that is, h is proportional to t squared. And using Galileo's principle, we can solve many problems for freely falling bodies. So using Galileo's principle, we're going to solve a problem. The problem is an object is dropped from a height of 100 meters. Now find out at what speed did it touch the ground. So we are given that height of an object is a is equal to 100 meters, the initial velocity u equal to 0, and final velocity, and we have to find out the final velocity at what speed did it touch the ground. So from Galileo's principle, we know that b squared equal to u squared plus 2g times h. So here is g is the acceleration due to gravity, and h is the height. Now we'll put the values in this equation here, and as we can see that initial velocity of an object is 0, and we can see that acceleration due to gravity is 9.8, and height of an object is 100 meters per second. So now we put the value here, and finally we find out that b squared equal to 1960, and finally b equal to 44.27 meters per second. So we can say that the object touched the ground at 44.2 meters per second. So now we're going to analyze, and we're going to sketch a graph from a given data. We can see there is a chart is given here, time, and in the right side there is a distance. It's a is the data of a car which moved in a certain time and the distance traveled by the car. We can see that at 0, when time is 0, the at the time 0, the distance of the car was 0 meter, and when time is 2, the distance is 6 meter. When time is 4 seconds, the distance is 24 meter, and at 6 seconds, the distance is 54 meter, and 8 seconds 96, and in 10 seconds, the distance is 150 meter. Now we're going to sketch a graph using these data. We can plot a graph using time versus distance. Quantities in every x-axis indicates the time, and y-axis indicates distance in meter. So here we can see that at 0 second, the distance of the car is 0. So here's the first point at 0, and in 2 seconds, the distance of the car, distance traveled by the car is 6, and we sketch the point here. And because we know in every x-axis indicates 1 second, and every ordinate of this axis indicates 10 meter. So here 6 is roughly here. So in 4 seconds, the distance traveled with the car is 24. We plot this point here, and in 6 seconds the car goes 54 meter, and in 8 seconds 96 meter, and in 10 seconds the car moves 150 meter. Now we plotted this point. Now we draw a line along this point. We see this graph here, and this is a time versus distance graph. Now from this graph we find out the time versus velocity. Now we sketch another graph here, which is time versus velocity, and we have to find out the average velocity from when at the beginning, when time is 0 and distance is 0. You can see there is no change in distance because there is no velocity here, so there's a origin. Now in 2 seconds, the distance traveled with the car is 6. The average distance is 6 divided by 2 is 3, and we plot this here at 3. And similarly, we plot the other time versus distance, and we can find out the velocity here is like this. And now we draw a straight line, you can see, and this straight line indicates the time versus velocity of this car. And this we solve when we sketch data from a given data.